Hey AP Chemistry students, it's your favorite chemistry teacher, Mr. Callenber. We're here to talk about some electrochemistry today. Volts and amps are two units of measurement we're going to use. And the coulomb is kind of an interesting idea. A coulomb is kind of like a mole, where it's a number of something, but in this case it's the number of electrons. Hey, there's your cell phone. How much power do you have left? We're also going to be talking about batteries. You can follow this lecture online at slideshare.net/Mr. Callenber, but I'm going to go through it all right here. The main guy we need to focus on here is Mr. Luigi Galvani. He's got some sweet hair there, looking good, pretty dapper. He was a biologist by trade, and was doing some dissections on a frog's leg, and noticed that if he touched it with two different metals, copper and zinc, the frog's leg would jump like it was alive. He went on to realize then that the muscles that we have in our body are controlled by electrical activity. And then we named the galvanic cell after him. It's just a fancy name for a battery. The good old book Frankenstein, I think you read that in 10th grade, was written by Mary Shelley after she heard about good old Galvani's work. Let's go on to Mr. Volta. That name should also ring a bell, the units of volts. He found that when you do put two different metals together, they decide that they'd like to exchange electrons. One of the metals will give up electrons, the other will take the electrons. And we've kind of already talked about this in our redox reactions. Oxidation is the loss of electrons, reduction is gain. Remember, if you lose electrons, it's oxidation. If you gain electrons, it's reduction. And what Volta put together is called the voltaic pile. I wonder why we call it a pile. Well, maybe because it's a pile of different metals separated by some electrolytes. What's an electrolyte? Simply a liquidy solution that allows the free flow of electrons, the free flow of electricity. So here's what happens in the voltaic pile. We've got zinc losing electrons, zinc being oxidized, copper gaining those two electrons, being reduced, and the flow of electrons between these two metals is a voltage. It's the flow of electrons. That's what electricity is. You always have a negative end of the battery called the anode, and the positive end of the battery called the cathode. Anode is where oxidation takes place. An-ox. The zinc is being oxidized. That's the anode. The cathode down here, cathode, is where reduction takes place. Cat-hode, cathode, reduction. Cat, red, an, ox. Cat, red, an, ox. It's another nice way to remember some of the terminology here. Hey, let's see what else SlideShare has for us. A variation of the pile is the Daniell cell. It's a pretty important type of a battery that was actually used up into the 1950s in the telegraph operator's station. It was a great way to easily supply electricity and to send that telegraph signal from one town to the next. Deet, 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 deet. You know what that sound is like. And it was a very easy way to see how much energy you had left in your battery. This is what the actual Daniell cell, also called a gravity or crowfoot cell. Gee, I wonder why they call it a crowfoot cell. Well, It's because the zinc electrode up there at the top looks like a crow's foot. The copper electrode down here at the bottom was in a solution of copper sulfate, and since that solution is more dense than the zinc sulfate solution up above, it would sink to the bottom and stay there because of gravity. So we have the zinc and copper gravity, crowfoot, or Daniell cell. So if you were the telegraph operator, you would sit there and send out your signals. Mom, we need bread. Please send us some bread. Whatever. As you were using up your battery, the zinc metal is changing into ions and going into solution. So this crowfoot here would get smaller and smaller and smaller as the battery was worn down. The copper down here, the ions would come out of solution as a solid piece of copper, and the copper metal at the bottom would get larger. This would get smaller, this would get larger. When the zinc was all gone, your battery was dead. So it was a very nice, easy way to see how much energy you have left in your battery, just like when you look at your phone to see how much battery you have left. The telegraph operator could just look at this and be like, oh, hey, we need some more zinc, or we need to take some of that copper out of there. So like it just says there, at a glance they could see exactly where they were with the battery's strength. I already mentioned why it's called a gravity cell. At night you recharge your cell phone. You're simply making one of these reactions run in reverse. So we've talked about the spontaneity of chemical reactions. The forward reaction is spontaneous. It happens all on its own. It gives off energy. And in a way, we're saying it's like exothermic. You can make the reverse reaction happen. You just have to put in energy. And that's what's happening at night when you charge your cell phone. You've used energy all day, and then you're making the reaction run in reverse at night. So what you should do right now is take a look at a standard reduction potential. It's in your AP information. I have a copy of it here. Just one second. We're looking at zinc and copper. So we've got copper ions changing into copper metal is a value of 0.34 volts. Zinc down here, remember we flipped this reaction around. We can't have reduction and reduction. We have to have reduction and oxidation happening. So when we flip this zinc reaction around, the zinc metal changing into zinc ions and giving off electrons, we're also going to change the sign of the voltage. It's negative 0.76, which turns it to positive 0.76. So when we go back to our crowfoot cell and look at those two reactions, combining them together now, we end up with the 0.34 being added to the positive 0.76, and that gives us 1.1 volts of electricity from this type of cell. So I just did the calculation for zinc and copper. What if we wanted to make a battery, say out of, let's use silver, which is 0.8 volts, And how about some magnesium, which is negative 2.37 volts. Magnesium and silver. Go ahead and calculate that voltage. Write your overall net ionic equation just like I did there, and see if you can calculate that voltage. It would also be good if you would write the oxidation and reduction half reactions. I'm going to pause the video, show my work. You pause the video, show your work, and then we'll compare our answers here when we restart this video.